Hello, everyone, and welcome to the joint seminar at the Thayer School of Engineering at Dartmouth. My name is Kofi Adamian, and I am the Program Area Lead for Electrical and Computer Engineering. And today, I'm excited and honored to introduce this week's joint seminar speaker, Dean Tsu-Jae King Liu. Dean Liu earned her BS, MS, and PhD degrees in electrical engineering at Stanford University. She was a staff member at Xerox PARC until joining the electrical engineering and computer sciences faculty at the University of California, Berkeley. And she is now the Dean of the College of Engineering at Berkeley. Dean Liu is internationally known in academia and industry for her innovations in semiconductor devices and technology, and she is highly regarded for her achievements as an instructor, a mentor, and administrator. She is an IEEE Fellow, a National Academy of Engineering member, a Fellow of the National Academy of Inventors, and a board member for Intel Corporation and a board member for MaxLinear Inc. Her awards and honors include the Intel Outstanding Researcher in Nanotechnology Award, the IEEE Aldous Van der Zeel Award, the IEEE Electron Device Society Education Award, and the DARPA Significant Technical Achievement Award for her role in the development of the FinFET. Now, you have to understand that the FinFET is an advanced transistor design used in all leading-edge computer chips today. You probably have FinFETs in your phones, in your homes, in your cars right now. And with that thought, I'd like you to help me in welcoming Dean Liu.
Thank you so much for that kind introduction and for the warm welcome. Good afternoon, everyone. I hope you can hear me, and I'm going to share my screen now. So it's my pleasure to join you all today. I really enjoyed my time earlier today with several of the faculty at Dartmouth and also learning about some of the really impressive work being done by the graduate students there. So it's my pleasure to spend time with you during the next half hour or an hour to share with you my perspective on semiconductor device innovation for the age, which makes possible the age of ambient intelligence. So I was told that not everybody is an expert in semiconductor devices. So I hope you don't mind if I sort of just provide some context for why I think this is an important or exciting topic of research. So we all know today that microchips are the brains of electronic devices. Pretty much any modern smart device has a microchip in it. And I think a lot of us are aware today that a lot of microchips are needed for things like automobiles, and the chip shortage has actually affected many industries, including the automobile industry. But essentially, microchips are really have transformed the way that we live in a modern society. They are the foundation for our ability to collect, store, and process large amounts of data, and to use it for useful purposes. Now, a microchip in our field is, for electrical engineers, we call it the integrated circuit. And so an integrated circuit comprises many components that are integrated together on a single substrate. It was first invented by Jack Kilby in 1958. Many years later, in the year 2000, he received a Nobel Prize in physics for that invention. And closely following him, Robert Noyce at Fairchild Semiconductor and later co-founded Intel demonstrated the first integrated circuit using silicon as the semiconductor material rather than germanium, which is what Jack Kilby used. In this dye photo on the right, the shiny traces are just the metal interconnects that are used to connect the transistors and the resistors on that IC chip. Now, for those of you who are not familiar with how integrated circuits are fabricated, they actually are not fabricated in chips, but on a large wafer. Today, the most advanced manufacturing facilities called fabs process 12-inch diameter or 300 millimeter diameter pieces of single crystalline silicon. And the chips are fabricated together all at once, one layer at a time. So an integrated circuit has many dozens of layers of material, semiconductor, metal, and insulator. And so they're deposited and patterned one layer at a time. And each pattern is defined by a mask. And the mask is designed by engineers and used in manufacturing by shining light through the mask and then focused onto the die location on the wafer. And there's some light-sensitive material that's coated on the surface that responds to the light pattern. And then we use that patterned light-sensitive material called photoresist to actually transfer the pattern to the IC layer. But today, a wafer can comprise thousands of chips, depending on how large they are. And each chip today has literally billions. I mean, the most advanced chips today have tens of billions of transistors. So you might have heard of Moore's law, which states that the number of transistors on a microchip, on the most advanced microchip, roughly doubles every 2 years. And if you look at this historical chart of the most advanced microprocessors produced over time, this is a logarithmic scale. So 50 billion is the count up here, and we are approaching that today with the most advanced microprocessors in past the year 2020. So this exponential growth in time has been called Moore's law, and it really is all about, so far, about transistors miniaturization. So we miniaturize a transistor, we can fit more of them on a chip, and if it's roughly the same, very roughly, the same number of steps needed to process a wafer, then you can actually fit a certain number of functions into a smaller area if each transistor is smaller. So you can fit more chips on a wafer, and for the same cost, you get more chips, so you can actually produce each chip more economically, right? So you can get lower cost. Or if you prefer to keep the chip size the same, you can fit more transistors on a chip, and you get higher functionality out of a chip. So no matter what, when you advance technology to be able to define finer and finer features, tighter pitch, you can fit more transistors on a chip. They'll either result in lower cost for a chip or higher performance and functionality. That allows designers to design new products that people will buy, and these make money and invest some of that money back into advancing the technology. So this virtuous cycle has gone on for more than 50 years now. But I think what people really care about is not necessarily Moore's law, but the impact on society of Moore's law. So if you look at the number of computing devices that have been produced in the world, roughly every decade you see an order of magnitude increase in the number of computing devices in the world. And today we are seeing, and this is because of increasing integration and increasing functionality of these computing devices. So we're seeing the emergence of the Internet of Things, edge computing as well today. So the interesting thing here to see is that the number of devices in the world today is, electronic devices is exceeding the number of people in the world today. So a fun fact you might not have heard before is that the number of cell phones in the world exceeds the number of toothbrushes, or actually no, the number of people who own a cell phone exceeds the number of people who own a toothbrush in the world. Okay, so it just shows you the ubiquity of computing devices today. And in the future, there will be many more devices than people in the world. And so this is where energy efficiency becomes an issue, because we will not be able to change the batteries or plug in every single device. And so I'll talk a little bit about that as a driver for further technology innovation going forward. Another interesting law that people have pointed out is the law of accelerating advancement. So as technology advances and computing power improves, we actually can make improvements in technology faster. So that's Kurzweil's law. You can see that the number of calculations per second for a given dollar amount has also increased exponentially over time, over the last 120 years. So over the last 50 or so years, this is mainly due to integrated circuit technology, microchip technology. But you can see that if we extrapolate, the calculation power of a human brain is going to be approached sometime within, I think, the lifetime of the people in the auditorium today, if not my own lifetime. So this is where we are all envisioning that there will be artificial intelligence that's going to be, ubiquitous. There'll be ambient intelligence. But there are some technological challenges for realizing that vision. So for the rest of my talk today, I'm going to focus on, some technical topics here. Just a quick review for those who are not super familiar with CMOS transistor devices and circuits, and just fundamentally why there's some limits to increasing the computing power just simply following transistor scaling. So then I'll give just a couple of examples of technology innovations that allow us to continue to improve computational efficiency, both time-wise and power-wise, and I'll conclude with a summary. Okay, so the tens of billions of transistors on a chip, on a computing chip today are mostly metal oxide semiconductor field effect transistors, or MOSFETs for short. And shown on the left here is a cartoon of a MOSFET. It's really just a three-terminal device. It's used as an electronic switch. You apply a voltage to the conductive gate electrode to control current flowing in the semiconductor between the source and drain electrodes. So the source and drain electrodes are heavily doped with impurities to make them electrically conductive. And the gate is electrically isolated or insulated from the semiconductor by a thin oxide layer, shown here in light gray. Now, the size of the transistor has shrunk over the years. So today, the smallest gate length is it's less than 15 nanometers. So that's about the size today. And ideally, it conducts current, like if you apply gate voltage higher than a certain threshold, current will start to flow. But if you plot the current on a logarithmic scale, you'll see that below the threshold voltage, some current does flow. The current changes exponentially as you change the gate voltage in this sub-threshold region. And the reason for that is because the physics of a MOSFET, is such that when you apply a voltage to the gate electrode, you are capacitively coupling to the electric potential in the semiconductor region underneath it. That's called the channel region. And ordinarily, the conductivity type, like if there's positive or negative charge carriers, is opposite between the source region and this channel region. So there's a natural electric potential barrier for electrons. So there are a lot of, let's say, electrons in the source because it's heavily doped with impurities. And those electrons are distributed energetically exponentially. So if you go higher in kinetic energy, there's exponentially fewer electrons. So only a small number of electrons will have enough thermal energy to overcome this potential barrier and go from the source to the drain if there's a voltage difference between the source and drain. But if you apply a gate voltage, when you apply gate voltage, you're capacitively coupling to the channel potential to lower the potential barrier. So as you lower that barrier, the number of electrons that can cross that barrier towards the drain increases exponentially. So that's why you have this exponential dependence of transistor current on gate voltage. Okay, and that this inverse slope of that subthreshold region is called the subthreshold swing. I'll come back to that later in this talk. And okay. So the key here is that the transistor is not an ideal switch. There will always be some non-zero off-state leakage current. In other words, there will always be some electrons that have enough kinetic energy to overcome this barrier when the transistor is supposed to be off, so that you cause unwanted leakage current to flow. And then the maximum voltage you apply to the gate, that determines how much current flows when the transistor's on. Now the on state, this is the drain. So the current flowing between the source and the drain in the on state is proportional to the width of the transistor. So the more cross-sectional area you have for current to flow, the more current that flows in the transistor in the on state. Also, the current is proportional to the velocity at which electrons are flowing from the source to the drain region. And that velocity is proportional to something we call the mobility. So that's proportional to that's a constant of proportionality to the lateral electric field. So the reason why electrons would flow from the source to the drain is because there's a voltage difference between the source and the drain that attracts the electrons to the drain, and that electric field causes the electrons to have some velocity. So the higher the mobility, the faster electrons drift from the source to the drain in the on state. And finally, the current is proportional to the amount of channel charge that appears in this region underneath the gate. So what happens is when you apply a voltage to the gate that's higher than the threshold, you attract a conductive layer of electrons to the surface. That's called a channel. And the amount of inversion, so the the channel conductivity type is the opposite of the substrate, so that's why they call it inversion layer. But the amount of charge in that inversion layer also determines how conductive the channel is. So we'd like that to be as conductive as possible. In other words, the charge in the inversion layer as high as possible. But then this is like a capacitor, right? You have two conductive electrodes separated by an insulator, and the charge on a capacitor is proportional to the capacitance and the voltage applied across it. In this case, it's the voltage above the threshold voltage. And in this case, it's the capacitance between the gate and the substrate. Okay, so that's really basic, but I'm going to come back to that those points later in just another slide or so. Now, the way that circuits work is important because if we want to innovate new devices, we have to understand how they are used in a circuit in order to improve upon the state of the art. So because there are two conductivity types, negative charge carriers or positive charge carriers, we have N-channel or P-channel transistors. The N-channel transistor only turns on when the gate voltage is more positive than the source by a minimum threshold. And a P-channel device, the transistor is on only if the gate is at a more negative potential than the source to attract positive channel, to cause a positive channel to form. Okay, so if you connect the source and the gates of N-channel and P-channel transistor together, like shown here, so these are just circuit symbols, then you get complementary behavior of the transistors. So that's why we call this complementary MOS devices and circuits, CMOS for short. So the most simple CMOS circuit is an inverter. You tie the drains of the N and P channel transistor together. The source of the N channel transistor is biased at the lowest potential, or ground, and the source of the P channel transistor is biased at the highest potential, or the VDD. That's what we call it. Now here, and the drains are tied together to form the output node. So if we have a low voltage applied at the input, let's call that logic state 0. The N channel transistor doesn't have a voltage difference between the source and the gate, so it's off. But the P channel device, you see the gate is at a lower voltage than the source, so it's going to be on. And so that's why the output node is connected to VDD through the P channel transistor that's on. So the output is high when the input is low. Now, if we increase the input to VDD, then that turns on the N channel transistor, causing it to discharge the output node so that it becomes 0, right? And then the P channel transistor turns off because now there's no difference between the gate and the source voltage. So the more current that the transistor conducts, the faster this node will discharge and the faster your circuit will operate. And this is the logic symbol to make it easier to draw something like this. Now, more complex functions can be achieved by connecting multiple pairs of N-channel and P-channel transistors. So in this example shown on the lower left, if we have, this is a NAND gate, so only if both inputs are high will you have both N-channel transistors turned on to connect the output to ground, to discharge the output to ground. So that's what's shown here. Both inputs high or logic level 1. That's the only time that the output goes low or logic 0. Otherwise, either one or both of these P-channel devices will be on to connect the output to the high voltage. Now, about half the area on a microchip today is taken up by locally storing some information, ones and zeros, high and low voltages. And the way that it's stored is usually with a SRAM static memory cell shown here. It comprises two cross-coupled inverters. So you can store a low voltage on one side and a high voltage on the other, or the opposite. But in other words, you can just store a 1 or 0, and this is a cell, a static memory cell. But in an array, rows and columns of these memory cells are usually arranged, and you can access the information through bit lines that are connected to the storage nodes by adding a couple of additional transistors, and these are called cascade transistors. So SRAM cell contains 6 transistors and is arranged in an array of rows and columns to store information, and you access it by turning on a word line, turn on these transistors, so that information is connected to the bit lines to be read out. Okay, so for a static memory cell, even if you're not changing the information stored, it's actually consuming energy. And that's because the transistors, remember the transistors each have non-zero off-state leakage. So there's always one of these transistors that is supposed to be off and the other one is on. So it will allow whatever current the other transistor wants to flow. And so any non-zero off-state leakage current results in static power dissipation. So take that current, I off times VDD, that's power dissipation right there. And so this is a fundamental challenge for integrated circuits today, as I'll explain in a little bit. But how do we get to where we are today to achieve nearly 10 nanometer short channel length devices? Well, we had to make innovations in materials and transistor structures like the FinFET in order to get to close to 10 nanometers. And this is because you have capacitive coupling between the gate and the semiconductor channel region to control the electric barrier for carriers to flow. But as you make the channel length shorter, you're bringing the drain and the source closer together. And remember, when the transistor is off, there's a large voltage difference between the source and drain. That's going to induce current to flow. And so if the drain comes too close physically to the source, the capacitive coupling between the drain and the source can start to affect that potential barrier. And so that's what is denoted here with the red curve. If the drain is too close to the source, then you actually lower the barrier. In other words, you're lowering the threshold voltage. So that's what's here. So ideally, your IV curve looks like this, but now you decrease the threshold voltage, and that causes the off-state current to increase exponentially, right? So that's not good, right? That's one of the short channel effects. So what we have to do to overcome this is to improve the capacitive coupling between the gate and the channel region, the semiconductor channel region, in order to make sure it's stronger, much stronger than the capacitive coupling between the drain and that channel potential region. So if you look at how the industry has scaled transistors over the last couple of decades, at the 90 nanometer generation technology, here's the gate electrode, here's the semiconductor and source and drain regions. What the industry first introduced was strained silicon technology, where you mechanically induce strain in the channel to either stretch it, to separate the atoms more, to make it easier for electrons to drift from the source and drain to the drain, or you compress it to make it easier for valence electrons to go from the source to the drain. In any case, you strain the silicon to enhance mobility to get more performance. Starting at the 45 nanometer technology node, the companies introduced high permittivity dielectrics between the gate electrode and the semiconductor to improve the capacitive coupling. That increases that reduces short channel effects, but also increases the inversion charge density. So that also improves transistor performance. And so there were a couple of generations of that. Now the FinFET, which Coffee mentioned earlier, was the next evolutionary step. If we can actually wrap the gate around the semiconductor rather than having it only on top, then we can actually increase the capacitive coupling of the gate to the semiconductor region here relative to the drain, right? If we reduce the cross-sectional area between the drain and the channel, then we can improve capacitive coupling between the gate and the channel. So this is the FinFET, and that's what it allowed the industry to continue to control the gate, the channel potential better, so you can turn on the transistor more steeply. This allowed the industry to lower the operating voltage, but still have good performance and still have good off-state leakage current to save like the battery life of your cell phones. Now, the only challenge with the FinFET is that, in order for this gate to have good control, you need to make the width of the fin smaller than the gate length. So that was a manufacturing challenge. Also, the width of the transistor now is the height of the fin. So that's also a manufacturing challenge, because if you want to make a transistor that can conduct a lot of current to make your circuits work faster, you would have to make a taller fin. So initially, what companies did was to increase the effective width, they would use multiple fins. So that increases the effective channel width. So you have more fins to conduct more current if you need it to have your circuit work faster. Now, over the decades, so FinFET was first introduced in 22 nanometer node. Today it's still being used at the 5 nanometer node. What companies have been able to do is to make the fins taller, and so that way you can reduce the number of fins, and therefore the layout area of the FinFETs has been reduced so that people can actually continue to shrink the die size. And then the next step, people expect within 3 years or so, is to evolve from thin body transistors to gate all-around transistors. So instead of wrapping the gate around 3 sides, you wrap around all 4 sides of the channel. People first demonstrated this many years ago, but the industry seems to be working towards sort of flat nanosheets with the gate electrode and the gate stack, wrapping around each of these sheets. So you can actually get a lot of effective channel width within a small layout area by going to nanosheets. So within the next 3 or 4 years, we expect to have nanosheets in production. Now, that's all about scaling down the channel length and controlling short channel effects and fitting as many, as much current in a given area as possible. But today, energy efficiency is becoming more and more of a requirement, especially for edge devices, IoT. So there's actually a fundamental limit for scaling the energy efficiency of CMOS. So if we look at, let's say, one of these curves here, this is a plot of the energy required per digital operation, computational operation, versus the delay, like how long it takes to perform that operation. So if you want to have your circuit operate faster, then you can operate at higher voltage to conduct more current so that you can operate your circuit faster, right? The transistor conducts more current. But that means it requires more energy because you need to charge up the capacitance to a higher voltage. And so there's always a trade-off. If you want to operate at smaller delay, in other words, faster, then you need to expend more energy. Or in other words, if you want to save energy, you need to operate at a lower voltage. And what the industry went to more than a decade ago is multi-core processing. So if you have multiple computational cores operating in parallel, they can each operate at lower voltage, and the throughput for the whole system, the chip, can still be improved. Right, the delay to perform a computation can be similar to what you wanted, but at better energy efficiency with multi-core processing. So this is really the reason why the industry moved multiple cores. And today, people are there are hundreds of cores on the most advanced like graphics chips. Now, but there's a fundamental limit here. Notice that this curve bottoms out, right? This can't go on forever, and let me explain why. So to understand why, we want to think more of how a digital computer is actually designed. You have a clock that sort of controls the speed at which computations are done. It serves to gate the various stages of the computation. You can model any digital logic circuit as a cascade of inverters. I mean, of course, these would be like NAND gates, but each inverter, so there's multiple stages of computation between each latch that is gated, that is controlled by a clock. And typically each of these gates is only switching less than 10% of the time. And then typically a fan out, like each gate might drive multiple other gates, typically 3 to 5, and the logic depth is usually over a dozen. Okay, so typically this is a generic model for energy efficiency considerations of a digital logic circuit. Okay, so let's try to understand why there's a fundamental energy efficiency limit. The total amount of energy needed to perform that digital logic computation, there's the energy needed to charge and discharge all of those capacitance at each node, input and output node of a gate. And that's proportional to the capacitance and the supply voltage squared. So we could save energy by lowering the operating voltage. And that allows us to lower the energy needed to charge and discharge all of those nodes in that circuit. But that means that we have lower on-state current. So that means your circuit will operate at slower speed. So the delay will be increased. Now, you can compensate for that by designing your transistors to have lower threshold voltage to get that high on-state current again, to get your circuit speed. But then your off-state leakage goes up exponentially. So, most of the time, those gates, they're sort of waiting for all the other stages to switch. So they're all the CMOS circuits are leaking, right? Leaking current. So this IV power consumption is happening. And the longer it takes for your circuit to work, then the more energy is wasted due to leakage. So you can see here then the total energy needed to perform any digital logic computation has some fundamental limit, minimum. And that is determined, that's due to transistor leakage, and that's related to the subthreshold slope. Okay, so eventually we can't continue to increase the number of cores in order to improve energy efficiency. We'll bottom out at some minimum energy efficiency. And so this is why for future logic switches, if we want to continue to fit more transistors on chip and lower the power consumption so the chips don't overheat, and so on and so forth, we actually need to come up with logic switches that turn on and off more steeply than a transistor. And that will allow us to come to a lower minimum on the energy versus delay curve. Okay. Now, fundamentally, the transistor today has, because of that exponential dependence of an electron density versus electron energy, we have a fundamental limit of 60 millivolts per decade at room temperature. And so we have to come up with ways to overcome that. So I'm just going to give you two examples. At Berkeley, we have Professor Saif Salahuddin, but he proposed this idea when he was a graduate student at Purdue University. The idea is simple, and I don't have time to go into detail. But if you add a ferroelectric layer, if you add that to the dielectric layer in the MOS gate stack, you can actually end up with sub 60 millivolt per decade switching behavior. So let me explain a little bit here. If you look at the energy versus charge for a ferroelectric capacitor versus a dielectric capacitor, they look different. Okay. But if you add them in series, you can actually end up with something like this. So what this curve showing energy versus charge stored is flatter, and that's effectively getting a larger capacitance. So you get better capacitive coupling between the gate and the semiconductor channel region. And in principle, if you perfectly match the energy versus charge characteristics of the ferroelectric layer and the dielectric layer, you can get a nearly flat curve. And what that means is that ultimately there's no really minimum gate voltage you need to apply to charge up the capacitor in order to turn on the transistor. And this was actually published in a review paper just a couple of years ago, showing this is a regular, MOSFET IV characteristic, and modeled with a ferroelectric inserted, you can actually get steeper than 60 millivolt turn-on voltage. And so this will allow CMOS circuits to operate at lower voltage, hopefully well below half a volt, which is kind of state of the art today. I'd like to lower it closer to like a quarter of a volt, and that will save a lot of power, right? Now, you might have heard of this. It's actually called negative capacitance MOSFET. And the reason for that is because the subthreshold swing, if you derive the equation for that, it's 60 millivolts per decade. In other words, in order to change the current by a factor of 10, you need to change the gate voltage by a minimum of 60 millivolts, okay? But if the subthreshold swing is less than 60 millivolts, that must mean that this factor here, this capacitance associated with the substrate, must be negative, right? So that's the effect. It's like, that's why it's called a negative capacitance MOSFET. And Professor Saif Salahuddin at Berkeley has been making really good experimental progress. The thickness of the gate dielectrics today is approaching 1 nanometer, and the ferroelectric that he adds is on the order of 1 nanometer. And that actually is good because you can actually get greater capacitive coupling between the gate and the channel region, but with a thicker material stack. And that actually helps to prevent leakage current between the gate and the channel, which actually can become a problem if the insulator is too thin. Okay, now my group has been working on mechanical switches for more than a decade now, so I'm going to spend the rest of the time today talking about mechanical switches. Now, we know that over the last few decades, there has been technology has advanced more than just following Moore's law. So your cell phones and other like game controllers and so on, and cars, the chips in cars do have mechanical devices in them today. They're used for your microphones. They're used for inertial sensors, like for sensing if you're tilting or turning, right? And there are other types of devices beyond CMOS transistors in electronic devices today. So let me talk about mechanical switch, because Fundamentally, that energy efficiency limit for CMOS is due to off-state leakage of a transistor. And so circuit designers, chip designers, have always asked this device physicists or device technologists to develop a switch that has zero leakage. And the only device that can achieve zero leakage is a mechanical switch, because you have a physical gap, air gap, between the two conductive electrodes, the source and the drain. And that's the only way you can get zero leakage energy. Now, a micro-electromechanical switch or electrostatically actuated switch is very similar, operates essentially the same as a transistor. You have a gate electrode, you apply voltage between the gate and the source that induces electrostatic force. And if the source electrode is compliant, then you can actually actuate it down into physical contact with the drain. So current can suddenly start to flow. And then when you have you have the switch in the on state, there's some contact adhesive force, right? Van der Waals force that holds those materials, those two electrodes in contact. So when you lower the voltage back down to reduce the electrostatic force, the spring restoring force of the deformed structure will cause the beam to actuate out of contact. But there's always some hysteresis because of this contact adhesive force. But we can engineer the contact adhesive force and the stiffness of the beam to make this hysteresis really small, or purposely to cause this switch to stick on, depending if you want non-volatile operation or volatile operation like for logic. So my group has gotten switches to work down to below 10 millivolts, switching voltage, and we've demonstrated circuits down to about 25 millivolts VDD. So you can get very low dynamic energy consumption as well as zero leakage energy consumption with mechanical switches. Okay, and there are other benefits of mechanical computing. They're radiation tolerant. They operate over a very wide range of temperatures. For transistors, the electron energy distribution is highly dependent on temperature, so your leakage current is exponentially dependent on temperature, and they are subject to irradiation as well. So, but then people ask, well, okay, how do you manufacture mechanical switches? I mean, transistors are so small today, they are so sophisticated. Mechanical switches are, old, right? We started, if you look at that Kurzweil's law plot, way back in the early 1900s, people were looking at mechanical switches. We went away from them for good reason, and that's because they were not energy efficient, and they were not cheap to make, not like, transistors today costing like nanocents. Okay, but if you look at CMOS technology advancement over the years, yes, we have made advancements in the transistor materials and structures, but we've also made advancements in the wiring. So today, a typical CMOS chip with 50 billion transistors has over a dozen layers of metal wiring, each patterned to interconnect the 50 billion transistors to achieve the function that you would like. And so over time, companies have developed this technology where you have air gaps between the metal wires. And that's because as the wires come closer and closer together, conducting, voltage signals, you don't want capacitive coupling between those signal lines. And one way to reduce capacitive coupling is to lower the permittivity of the material between the wires. So air has the lowest permittivity. And so today's most advanced chips do have air gaps between metal wires. Now, to make a mechanical switch, all you need is a movable electrode and air gaps, right, to allow some movement. So we can adapt a modern day interconnect technology to form switches right on over the CMOS transistors. Now, switches don't turn on and off as quickly as electronic transistors. So we would like to use them in a different way than transistors. Let's think of them as mechanical switches as reconfigurable interconnects. So the slide I showed earlier, CMOS transistors interconnected different ways. The interconnections actually determine the functionality of your chip, right? So if you can reconfigure the physical wiring of your chip, then you can actually adapt the functionality of your chip over time. So here is just a simulation showing how one mechanical switch could be designed. You have multiple layers of metal and vias to interconnect those layers. We can actually pattern the metal and vias to form a movable beam like this, anchored at the bottom. And then on either side, we can pattern electrodes to induce electrostatic force to attract them to the right, the beam to the right or to the left, into contact with a conductive electrode at an upper layer on the right or the left. Okay, and if you engineer this so that the contact adhesive force is larger than the spring restoring force of the beam, then you can make the beam stick in the conductive contact state. So one of my PhD students has worked with standard foundry processes. Okay, conventional CMOS manufacturing process. What she's done is she's used the standard process development kit to design the metal layer patterns, to pattern them so that they form that switch that I showed on the previous slide. And using the most tightly spaced metal layers to form the switch, and then the upper layers can be patterned to form a mask, so that after we get the chip back from the foundry, we can just naturally subject this chip to an etch process to remove the dielectric layers like this on either side of the beam, and these upper metal patterns form a mask for that etch, so we can release that. So shown here are a plan view scanning electron micrograph images of that switch. Here's the movable beam. It can either be actuated to one side to contact, or the other, shown here after actuation is in contact with the D0 electrode. And here's a different cross-section showing the beam and the conductive electrodes on the upper layer and the actuation electrodes on the left and right sides. Now, the amount of voltage needed to actuate those beams is actually quite large, not compatible with transistors today. But if we scale down, if we use a more advanced technology with tighter and tighter pitches, so the metal lines are really close together, then the air gaps are smaller. And so for this, you can use less voltage to induce the electrostatic force or the field needed. So as you scale down the pitch and the spacing of the metal wires, you can achieve lower switching voltages. So we project that beyond the 7 nanometer generation of technology, these back end of line metal switches can actually operate with CMOS compatible voltages. And the experimental data and the simulation data are consistent. So we know that if we can just advance the technology node further, we can get down to below 2 volts, which is what is CMOS compatible. Okay. Now, so what can we use this for? Well, we can enable new computing architectures, right? We don't want to do things the same way as CMOS because mechanical switches are slower, so it doesn't make sense to have those multiple stages of logic and so on and so forth. So here's just one example. We can actually implement I think this is a decoder circuit. So depending on the input signals, 0, 0, 0, 0, 0, 1, 0, 0, 1, or 1, 0, we pre-program this array of switches to contact either data 0 or data 1 line. And then once you provide some input voltages, only one of these output lines is going to be driven low. And so this is essentially a decoder function implemented with mechanical switches. And the CMOS buffers, so these diodes are just semiconductor diodes at the bottom, located at the bottom of these switches. And because of the diodes, there's some voltage drop loss. So the CMOS buffers are required to sort of restore the output voltage to the full VDD. But maybe a more interesting example that we published last year is that essentially the same decoder circuit on the left. This decoder circuit only allows one of these bit lines to go low, and corresponding to a certain input address. So that if you use that low bit line to sort of discharge some output lines, you can actually implement a lookup table. So rather than calculating the answer to a problem, right, by inputting lines and then doing all those logics, gates, you can actually just input the address and look up the answer. So this saves time and energy. And so bottom line is my student demonstrated a functional lookup table implemented with CMOS buffers and with mechanical switches, all stacked on top of each other. So you save area. So you look at the area, the readout delay, the readout energy is orders of magnitude. These are each orders of magnitude. So for the mechanical switch array, CMOS plus NEMS, we can actually save a lot of area, chip area, because for a CMOS implementation, you actually have to read information, the stored information or the stored answers from a non-volatile memory chip onto the SRAM array on your chip, and then input the address and read out the answer. Here, what I showed earlier, you have mechanical switches over CMOS, very compact. You input and you read out the answer. So you save a lot in chip area, therefore cost, and also the time needed to read out the answer and the energy needed to read out the answer is orders of magnitude better than conventional CMOS. Okay, final example. That was sort of making use of the interconnect layers to implement greater functionality, but you can also add more devices on top of CMOS. So here is an example where my group integrated just a mechanical switch over a conventional CMOS circuit. And the way that this switch works, again, it's pretty simple. You apply voltage between the gate and the source to induce electrostatic force to bring the source and drain into contact. Actually, what we've done is we enhanced this. We used a fourth terminal called the body. So it's the voltage difference between the gate and the body that determines if the source and drain are going to be in contact. Okay, so notice though, in this design, there's electrostatic force induced between the gate and the body, and also electrostatic force induced potentially between the source and the drain to bring this structure into contact. Okay, so why is this interesting? Now, mechanical devices like musical instruments and so on naturally are physical oscillators, right? So if we apply a voltage between the gate and the body of that four-terminal relay to just barely turn it on, like not even try to not really turn it on, we can actually bring it almost into contact. And then we apply a voltage to the drain through a resistor like this, that extra electrostatic force between the drain and the source can be enough to turn on the switch. Okay, so originally when you apply a voltage to the drain, it's a high voltage, but then the switch turns on to discharge this drain, and that reduces electrostatic force, but then that causes the relay to turn off. But then the voltage charges back up, and so the relay turns on and off just by applying DC voltages. And we are going to present this at the IEDM conference next month in San Francisco. If you this is just showing experimental results. If you ramp up the drain voltage, you start to see the drain voltage, the VDD here. You start to see is that right? Yeah. You start to see the drain voltage oscillate like I showed here because of this self-powered oscillation. Now, in this paper, we're going to show that we can actually synchronize that oscillation to a signal that has twice the frequency. So this phenomenon is called subharmonic injection locking perturbation, or SHIL. So if you have this perturbing signal that's at roughly twice the frequency, then you can get this oscillator to synchronize with that signal. But there's two possible phases that can be synchronous with this SHIL signal. So these two phases are exactly 180 degrees out of phase. So you can encode information not as high voltage and low voltage, but you can encode it as 0 degrees phase and 180 degree phase. So my students will publish that in IEDM next month, but we've demonstrated that we can actually do the subharmonic injection locking with this kind of a relay oscillator. And it's interesting because it can enable a new type of computing architecture. One example is the so-called Ising or Ising machine, depending if you're German or not. So it turns out that a lot of problems, like for AI, are like combinatorial optimization problems. Like you have a bunch of nodes. You can map a problem onto a network of nodes, and each node can either be a 1 or 0. How do you optimize the overall combinations of ones and zeros? Well, if you map it onto a physical network of oscillators, and oscillating, so a network of oscillators naturally will settle at a lowest energy state. Okay, so if you can actually encode your problem, your combinatorial optimization problem, into a physical network of oscillators, where the strength of these interconnections is mapped onto the edges of your network, your network graph, you can actually arrive at a solution with much lower energy and much shorter time than any conventional logic, CMOS logic implementation. So this is why we're interested in mechanical switches also, because they enable they have functionality beyond a transistor, and therefore, if we can leverage their behavior, we can achieve much better energy efficiency and speed. All right, so the idea here is that the oscillators will settle within about a dozen cycles, is what we've seen experimentally, with binary phases, either in or out of phase, representing the minimum energy configuration. Okay, so to conclude, device innovations will continue to allow us to continue that Kurzweil's law, so we can extend the scalability of CMOS and also the functionality of CMOS-based ICs to enable new computing paradigms. So this virtuous cycle, I think in the future, we'll more and more rely on not transistor scaling, but device innovations for improved functionality and better energy efficiency. And that's what's going to drive this virtuous cycle to allow us to achieve or realize the vision of ambient intelligence, where we have smart systems embedded in us. We're talking about implantable devices earlier today, in people, in cars and buildings and structures. So we can, for future smart cities, for smart medical or healthcare, smart transportation and smart manufacturing. So that's basically the conclusion. And I'd like to just acknowledge all the students and collaborators that made this work possible, and the companies with whom we worked to fabricate the CMOS and NEMS chips that I talked about earlier. And we have a nice nanofabrication lab at Berkeley where we do a lot of this original FinFET work and the relay work, and wouldn't have been possible without support from companies and agencies like the NSF. So I'd like to just conclude there. Thank you for your kind attention, and I'm happy to answer your questions.